PowerPoint.
Okay, so thank you very much for your nice introduction.
Thank you.
Also, thank you to SECPHO for the opportunity of being here, presenting some solutions we have in the Terahertz regime. First of all, short introduction about Grupo Alava. Grupo Alava is a group of companies. We have offices in Spain and Portugal mainly, but also in the United States and in Peru. And the main core business of our company is distribution of products. We have different departments trying to cover with a wide range of products all the needs of our customers, made in Spain and Portugal, and of course solving any issue related with service and post-sales processes. Some companies of the group they are in charge also of diagnostic services related mainly with civil engineering and predictive maintenance of different industries. We also develop solutions by integrating the hardware we distribute and also by developing software applications specific for certain customers. And finally, we have an innovation department. They evaluate our participation in projects and collaboration with research centers and companies in Europe. I'm part of the photonics and nanotechnology, let's say, division. We try to be a global supplier offering to our customers all the systems they could need. We divided the solutions in three main brands, so nanofabrication, nanocharacterization, and the spectroscopy solution. And we have in the last years been working a lot with Terahertz. That could be something between nanocharacterization and spectroscopy. We see more and more interest here in our country for Terahertz solutions, mainly in R&D, but also more and more in industry. And we can offer here Terahertz imaging solutions. We work with our partner I2S from France, and also time domain spectroscopy developed by our partner Menlo Systems. I will talk about both of them. And also why Terahertz? Well, following some comments from the previous talks, Terahertz they have some interesting properties. So it's low energy, it's non-ionizing, so for the investigation of some kind of materials is safer than X-ray, for example. Penetration is interesting in non-polar materials, like plastics, like rubber, like ceramics. They are also directional, so we can use optics with the lenses to focus in certain point of the sample, to use optics in the case of the cameras. So we can use the things we know about visible optics to work with the Terahertz. And also it's interesting because solids, liquids, and gases often receive some signature fingerprint in the Terahertz brand. Of course, there are some limitations. For example, water is a material that absorbs strongly this radiation. So components with a lot of water could be a problem. We can use this property in case of a small amount of water, but could be a problem. And also it's reflected by metals. The solution is linked to the wavelength in the order of millimeters of 2 millimeters, and also the Terahertz waves transmitting there. But in case of high humidity, talking about water again, they are strongly attenuated. So let's talk about the first technology we distribute in our country, that is time domain spectroscopy in the Terahertz regime. As I mentioned before, this product is developed by our partner Menlo Systems. It's a German company that manufactures femtosecond fiber lasers, the Terahertz solution, and also frequency comms. In fact, this is the main product. The founder received the Nobel Prize in 2005 for the development of the optical frequency comms, but with expertise in short pulse lasers, they have also worked a lot in Terahertz. This is a system similar to the one presented before. We have two photoconductive antennas, one emitter and one detector. As I mentioned before, we can use optical elements to work with the beam, to focus the beam in the sample, to manipulate the beam. And we need ultrafast laser to generate pulses that, on one hand, goes to the emitter antenna to generate the terahertz radiation, and on the other hand, with the optical delay unit, goes to the detector to ensure the detection of this radiation. Normally, the signal we receive in the detector is quite low, so we need an amplifier to have the final signal. And this is the generation. I think it was already discussed, but the principle is the generation of charge carriers by the laser pulses when reach the emitter antenna. They are accelerated by the bias connected to the antenna, so it can emit terahertz. And in the detection, the terahertz field is the one accelerating the charge carriers. And when we get the pulse from the laser at the same time as the terahertz pulse, we can get this photocurrent that can be measured using an amplifier, as I mentioned before, because it can be a weak signal. This is the more detailed process, and why we need the optical delay unit is because we need to play with the moment that the second pulse, the gating pulse, reach the detector to have a signal, and moving this delay unit, we can control the moment where both pulses reach the detector at the same time. So depending on the absorption of the material at the time the terahertz pulse passes through the material, we can detect the signal. In this case, we have a signal that is intensity with the time, but we can transform it with a Fourier transformation in a spectrum in terahertz. This is the signal we normally have. An example on a couple of materials is a photocurrent with the time. So we have a couple of pulses depending on the material, and by FFT we can transform it in a signal with certain amplitude related with the frequency where it is detected. And this signal can be related with the parameters of the material. Talking about the systems, Menlo developed this research system. We can see the components I described before. We also can include a second harmonic generator. In some applications, it is interesting also to have the secondary harmonic, for example, in pump probe to excitate some kind of materials. And with this kind of systems, they can cover a broad bandwidth up to 6 terahertz, and with that scan window between 805 and 1600 picoseconds. This system can be used both in reflection and transmission, and we can make some kind of imaging. It's not real imaging, but we saw the antennas. It's a point-by-point detection, so with a XY stage, we can get also an XY picture of the material, and may have a representation of how the terahertz waves passes through each point of the material. In going through the industrial part, they have developed a more compact system. All the electronical elements, laser and so on, is included in a rack that can be easily installed in any kind of system, and we just need the connection through optical fiber to the antennas to reach the material. And the characteristics of the systems are quite similar to the lab one. Menlo have been participating in different industrial projects like witness detection also, and also seed grading, but I want to show you some pictures of the measurements they perform in plastic materials, as I mentioned in the title. For example, this is a kind of measurement in polyethylene foams used to cover the coal cables. We can see that the terahertz, transmission terahertz, allow us to distinguish which foam have the wires inside and which one is without the wires. Also working or playing with the polarization, we can distinguish different structures, internal structure of the foam. We can see the effects depending on the polarization. So it's a quite powerful tool. We can also use the software to get more precise measurements of the internal structure and distinguish which part is related with the foam and which part is related with the metal. In this case, we use the transmission in the foam versus the reflection in the metal to have this picture of the structure. Another application, interesting application, is to distinguish the composition or the presence concentration of polymer fibers in certain samples. Terahertz can be used to distinguish the amount of pressed propylene that was used in the sample. We can see the picture that with a visible picture there is no difference between the areas, but they have been manufactured with different amount of fibers. This amount of fibers is shown in the terahertz image, so it can be used to distinguish between different materials. There is also a project to work in the orientation of fibers, playing with a refractive index. There is not much information as in this project, but the idea is to have an idea of how the fiber orientation changes with the terahertz polarization, and it's visible with terahertz. And the last example I want to show you about the time domain spectroscopy is how to evaluate the plastic joints. We can see here a couple of examples. One is made with metal wires drilled in the material, and another couple of plastic pieces root. And terahertz allows us to see the dimensions of the wires that have been used for performing the joint. And in the case of the glue, we can see also bubbles. We can see also some defects in the joint. So it's like a tool for evaluation of the joint. And the second part of the talk is about properly terahertz imaging. We talk about some kind of imaging we have with the XY stage in the point-by-point detection. But we also work with the Y2S. This is a company based in France that started with a project in 2006 with the Castelo project, and started working with the SIA-led group developing a terahertz camera until in 2017 where they present this commercial camera. And you can see here the products they have nowadays. They are cameras based on a micro-volumeter technology, covering also a broad spectral range from 0.1 to 5 terahertz, and they have a couple of systems depending of the power needed on each application. As I mentioned, the detection is based on a volumeter technique, so it's something like in the infrared cameras. They have a couple of antennas deposited in a suspended membrane, and then they can measure difference in temperature when the terahertz radiation reaches those antennas. Also talking about cameras, it's important the objective lens. So Y2S also offer a couple of options of objective lens to reach each application. There is also an important point, that is the illumination. With these kind of cameras, we normally use Schottky diodes or quantum cascade lasers for illumination, but it's important to choose the right source. Can be continuous wave, can be pulse, or single wavelength, to be sure that the performance of the system is respected. And you can see here pictures of different beams from the different lasers, because it's also one of the main applications of the cameras is characterization of this kind of terahertz beams. Talking about samples in plastic, you can see here first a couple of samples. Terahertz camera allows us to see the internal structure of samples, and we can also distinguish differences in thickness in the pieces, in the internal part. In this case, it's a working frequency of 2.5 terahertz. Here we have another example, internal defect detection, defects that are not visible. They can be identified by the terahertz image. And also an example of thickness variation. We can see how the contrast is quite different depending on the thickness of this plastic piece made by injection molding. Here I have a video. I hope you can see it about also a sampling, a plastic part, sorry, that is measured with the Terahertz camera, and we can see the different components inside the piece, and also the effect of the thickness of the piece when the piece is rotating. This is quite interesting technology for this kind of application. And finally, in some way related with plastic, or because the external material of this cases is made on plastic. Terahertz, of course, was always related with security, and so security is also one important application. And we can see how can we detect hidden objects inside plastic cases. In the left we have a metal key, and in the right we have something like a syringe. And the terahertz allow us to see this kind of forbidden products or dangerous elements inside these cases. So security, of course, is one of the main applications of this technology. And thank you very much. I hope it was interesting. Well, ready for questions if you have any.
So thank you very much, Antonio, for your summary of the two different approaches for imaging and spectroscopy. I see a question here from Elena Martinez, who is wondering what's the cost range of this sort of cameras.
Well, this is perhaps something to discuss more in a private conversation. But let's say that it's something between 50K and 100K. Also, the important part is illumination. Depending on the application, illumination could be even more important than the cost of the camera.
So these cameras are cameras that you fully develop yourselves?
It was developed by I2S, this French company. So yeah, you can go to their website and see the product range they have, and then question you can address through me or through them. It's a quite interesting product.
And what is the resolution you can achieve with these cameras?
But I think I don't have this value resolution right now. We can ask Y2S colleagues. I think there is a colleague of my Y2S is here. Amalia is in the chat. I don't know if she wants to answer. If not, you can contact me through my mail, then we can find the resolution.
Okay, sounds very good. Very interesting talk.